Neutron stars are among the most extreme objects in the universe. They are like giant atomic cores. These stars are kilometers in diameter, incredibly dense and violent. But how can such objects exist? The life of a star is a delicate balance of two powerful forces: its own gravity pulling inward, and the outward radiation pressure generated by its fusion reactions in the core.
In the core of stars, hydrogen atoms fuse into helium, releasing immense energy.
Eventually, the hydrogen fuel in the core becomes exhausted, leading to further fusion.
If the star is massive enough, helium now fuses into carbon, then neon, oxygen, and silicon.
The star's core becomes layered like an onion, with heavier atomic nuclei building up at the center, until iron is formed. Iron cannot fuse into another element, so the fusion reaction stops. The radiation pressure drops rapidly. The star is no longer in balance. If its core mass exceeds about 1.4 solar masses, a catastrophic collapse takes place. The immense pressure overcomes the quantum mechanical repulsion of electrons. Electrons and protons fuse into neutrons. The matter becomes incredibly dense, packed as tightly as an atomic nucleus, forming a substance called neutronium.
The outer layers of the star are catapulted into space in a violent supernova explosion, leaving behind a neutron star.
A neutron star's mass is between 1 and 3 times that of our Sun, yet it is incredibly compact.
It's compressed to an object only about 25 kilometers wide, similar in size to a small city.
To give you perspective, a neutron star has roughly the diameter of Manhattan. It's so dense that 1 cubic centimeter of neutron star material has the same mass as an iron cube 700 meters across. That's roughly 1 billion tons, equivalent to the mass of Mount Everest, compressed into a sugar cube.
The gravity of a neutron star is incredibly impressive. If you drop an object from just 1 meter above its surface,
It would hit the star in 1 microsecond, accelerating to 7.2 million kilometers per hour.
Its surface is extremely flat, with irregularities of only 5 millimeters, and it has a super thin 10 centimeter atmosphere of hot plasma.
The surface temperature is about 1 million Kelvin, significantly hotter than our Sun's 5,800 Kelvin.
Let's look inside. The crust is incredibly hard, likely made of an iron atom nuclei lattice with electrons flowing through it. Deeper in the inner crust, we find more neutrons and fewer protons. The outer core is a dense soup of indistinguishable neutrons. The core of neutron stars is very, very strange. We're not entirely sure of its properties. Our best guess is superfluid neutron degenerate matter, or ultra-dense quark matter, known as quark-gluon plasma. This matter doesn't make sense in traditional physics, and can only exist in such an ultra-extreme environment. In many ways, a neutron star is like a giant atomic core. The key difference is that atom cores are held by strong interaction, while neutron stars are held together by the immense force of gravity. Neutron stars spin incredibly fast. Young ones can rotate several times per second. If there's a nearby star to feed the neutron star, it can rotate up to several hundred times per second.
Like PSR JS 1748-2446 AD, which spins at approximately 252 million kilometers per hour.
This speed distorts the star into a strange, oblate shape. We call them pulsars because they emit strong radio signals.
The magnetic field of a neutron star is roughly 1 trillion times stronger than Earth's, bending atoms that enter its influence. Neutron stars are truly extreme and cool objects. Hopefully, we'll one day send spaceships to learn more and take pictures. But we should always remember not to get too close.